Okay, good morning. First of all, I want to thank the organizer for this nice meeting and for the wonderful science that we had here. Actually, I was amazed by the amount of nice science that we have in the Nano Center. So I'll be talking about electron-doped cuprates. It's not really a nanoscience in the sense that we are making nanoscale devices, but I will try and show you that there are scales here on the nano size that we may be able to control, and these scales actually control the properties of the cuprates. So I'll focus on electron-doped cuprates, and okay, and we'll see. So let me see if I can. Okay. So the cuprates were discovered 21 years ago by Bednorz and Muller, and they are very special materials. And now people can make amazing things with these materials. For example, this is a. Okay, let's see. This is a ship propulsion motor. And it's made out of ITC superconductors. And this is actually thanks to nanotechnology. These cables are made with specially designed self-assembled nano defects, and then they can withstand high magnetic fields and very high currents. But I will not be focusing on that. I'll focus on the properties of the... it's cooled by nitrogen, or it's actually a huge cryocooler. But since this motor is so big, they can neglect the cooling power compared to the amount of power that they save when using the superconductors. And basically, this motor is extremely efficient when let's say, the aircraft carrier is traveling slowly in smooth waters. So, and this is what they usually do. They just move from the United States to Iraq, preparing for a big war, and then they can save a lot of energy that will be spent later. Okay, so basically there was a tremendous increase in TC until, let's say, 1990, and now it's about 140, and we're stuck there. It's also 140, and excuse me for the Chinese here, and 140 in Celsius and Kelvin, so you can remember that. Oops, wrong button. Okay, so what is so special about the ITC cuprates? First of all, they are quasi two-dimensional. Everything takes place in these copper-oxygen planes. TC, I mean, the critical temperature depends on the number of carriers that are put in the copper-oxygen planes. And they have an exotic superconducting state. You know that superconductivity is now solved for 50 years, but not in these materials. And they have a very special normal state. Let's look at the properties of this two-dimensional, of this plane, of the copper-oxygen plane. So this is the copper-oxygen plane. First of all, the parent compound is antiferromagnetic. If we look at it in terms of band theory, then basically the copper orbital is not full, so it should be a metal. But the parent compound is actually an insulator, so if one calculates the properties by naive band theory, then the success is very limited. And basically it's a Mott insulator, so there are strong correlations and the Coulomb interactions, and it is an insulator. Now we can change the properties of this insulator by putting charge carriers in the copper-oxygen planes, and these charge carriers can be holes, such in lanthanum, strontium, copper-oxygen. So lanthanum is replaced by strontium, and then you add holes. Or, for example, in praseodymium or neodymium, cerium copper-oxygen, so the rare earth praseodymium or neodymium is replaced by cerium, and then you add the whole electrons to the copper oxygen planes. So these are electron-doped, and these are hole-doped, and I'll be talking mostly about these guys, which are less popular, but they have few advantages. And this is the phase diagram. Basically, this is the dopant concentration. It can be strontium or cerium on this direction. And let's look at the hole-doped. So here it's an antiferromagnetic insulator, and then you put more charge carriers, and then superconductivity onsets. And this is the optimum doping, where TC has a maximum, and this is the overdoped side and underdoped side. And here there is a very weird phase that we call the pseudo-gap, and that the material shows very weird properties. And on the overdoped side is kind of a normal metal, maybe. And this is the electron-doped. There is a broad antiferromagnetic region, maybe persisting into the superconducting region, and a very small superconducting region. And I'll try and discuss why this region is so small. Okay. A nice thing about the electron cuprates, electron-doped, is that usually one needs 100, if you want to look at the normal state, usually everything is obscured by superconductivity. If you want to measure resistance, for example, or thermal conductivity, everything is obscured by superconductivity. So if you want to look at these properties, you have to quench superconductivity somehow, and usually you need 100 Tesla. But in the electron-doped cuprates, 10 Tesla is enough, and this is the hybrid magnet in National High Magnetic Field in Tallahassee, so you don't need this. You can use a lab magnet, and the normal state is accessible. Now we want to look at the properties of the normal state here, and see actually if the or some kind of antiferromagnetism persists into the superconducting dome. So this we did a while ago, and basically you just quench superconductivity and you look at the normal state here. So we found some evidence that actually there is a phase transition, quantum phase transition in the transport and in optics. For example, the Hall coefficient changes sign and changes behavior here near optimum doping. This is in the normal state, but at very low temperatures, at 350 millikelvin. There is a magnetoresistance that is a spin-related magnetoresistance that vanishes around 0.15 near optimum doping. And in optics, there is a gap that goes away around the same thing. And basically, this summarizes everything. So here there is a region where the resistivity has an upturn. It increases when the temperature is decreasing. Here there is a weird exponent in the resistivity. And here the Fermi-liquid behavior, or kind of Fermi-liquid behavior, is recovered. So maybe there is a... Excuse me?
Typical optical gap. You say in optics is a gap.
Yeah, it's about 100 millielectron volts. Depends on the... It closes with when the doping is increasing. So here the gap is 0 and increases here. So it's a significant gap. So what this thing may be, it's some kind of antiferromagnetism. This is mu-SR. So this is old mu-SR data, and this is the superconducting dome sketched with hand or with the computer. And Newton scattering shows that there is no antiferromagnetism here and some sort of antiferromagnetism here. So maybe the antiferromagnetism is going away around 0.15 behind the superconducting dome. And this is the Fermi surface. Basically, this is the ARPES measurements. It's a photoemission. Basically, it's a photoelectric effect with the K resolution. So one can look at the Fermi surface. And here you can see that the Fermi surface changes with doping. So this is very underdoped. In a very underdoped, it's an electron-like Fermi surface. And the Fermi surface consists actually of small electron pockets. And then something goes on here. And still you can see these electron regions, and this is optimum doping, and you see that the Fermi surface become circular-like. Still there are these gaps here, and these may be the gaps that are seen in optics. So basically the Fermi surface undergoes some reconstruction when the doping is changes. So it changes from electron-like to hole-like Fermi surface, and this is what we see in the transport and the optical experiments. Maybe the same thing is going on in hole-doped cuprates. Actually, this is a very recent work just put on the archive. So this is Shubnikov-de-Haas oscillations. Basically, you look at the magnetoresistance or in the Hall coefficient. So, and the Hall coefficient oscillates. There is some oscillation in the Hall coefficient. You can see them here, and after the background is subtracted. And the period of the oscillations, or the magnetic field, is related to the size of the Fermi surface. And these are actually underdoped samples, very clean. And you can see that, that there is a Fermi surface, which is actually surprising. It should be some kind of an insulator. And there is a Fermi surface, and it is very small. And maybe it is electron-like, because if you look at the Hall coefficient, it is a negative. So the slope here is a negative. So maybe the same thing is going on in the hole-doped cuprates. So there are electron pockets, and then when you change the doping and you go into optimum doping, it changes into hole-like Fermi surface. Okay, but this is just a speculation. What about the superconducting state? So this was just a review about the normal state. And now a little bit at the work that we've done recently in the superconducting state. And basically we did some tunneling experiment. In a conventional tunneling spectroscopy, you know that when you try to cross a wall with a ball, it won't work, but for electron it works. And you can actually look at the density of states when you deposit an insulator on top of your superconductor or whatever you want to look at, and then you measure the currents versus voltage. And this is all techniques invented by Ivar Gever. And here you can see the spectrum of lead. So this is the peak in the density of states predicted by BCS, and these are the lead phonons. So everything is nice and clear, and here the IDV is proportional to the density of states, normalized with the density of states in the normal state. And he got the Nobel Prize for this. So basically we want to ask a few questions. One question is, what's the pairing symmetry? For example, basically this is the potential that these Cooper pairs that Guy Deutscher talked about 2 days ago, the potential that the Cooper pairs see. So it can be isotropic, which means it doesn't change with K. I mean, it doesn't matter where the electron is traveling to, and it will see the same potential. Or let's say a D wave, then it changes like cosine 2 theta. It's two-dimensional, so it changes sign and amplitude when you look around the Fermi surface. And why is it important? It is important because this potential delta, or the order parameter, is related to the interaction through the BCS equation. So this is the interaction that causes superconductivity that we want to find. Basically, this is the most the unknown thing in these cuprates. Now, in electron-doped, as I show you, there are these gaps here, or we call the hotspots. So a lot of scattering is going on here. So one expects that the order parameter will change. I mean, if the superconductivity is related to this scattering, then the order parameter will be modified slightly compared to hole-doped. And indeed, this was observed by Gersh Blumberg from Bell Labs, and he actually suggested this non-monotonic D wave. Basically, instead of peaking here, the gap peaks here, or if you want, you put higher harmonics in the expansion of the gap. Okay, so the question is whether this is seen in the entire doping range. Question number 2 is what is the nature of the transition temperature? In a conventional superconductor, as you increase the temperature, this order parameter just goes to 0. So basically, the pairs are formed and condensed at Tc. So there is this pairing potential that suddenly appears, and also the pairs appear, and then there is a condensation, BCS condensation, and you have coherence. Now, in high Tc cuprates, this is an experiment done by Renner and Fischer. If you look at this gap, this is Tc, and the gap just persists well above Tc. This is up to 300 Kelvin, and you see this gap going on at high temperatures, and there is no significant change when one goes above Tc. And this is what we call the pseudo gap. So the question is whether this is also seen in electron-doped cuprates.
Why do you call it pseudo gap?
Because you don't have superconductivity. And
It's a gap. You have a gap also in normal
yeah, it's a gap.
semiconductors.
Yeah, it's not exactly the same thing because it's not a zero. It's not like in semiconductors that you have a band gap or something. It's you see it. It's a spin gap. You see it, for example, in when you measure susceptibility, or when you measure this tunneling spectroscopy. But the origin is actually unknown. What is the origin of this pseudo gap? Okay, so, excuse me. Okay. So there are two scenarios for this critical temperature. One is a competing order. So there is a competing order. Let's say this some kind of antiferromagnetism competes with the superconductivity, and then a quantum critical point at some point. Or superconductivity can be gone because of phase fluctuations. So the amplitude of the superconducting gap is a constant, but there is the phase is fluctuating, and then the order parameter is there is some gap, but the coherence is gone. Now I want to talk about two length scale that we want to look at. So one length scale is the coherence length, which turns to be very important. So if you have a gap, usually you have a length scale that is associated with. And for superconductivity, this length scale is the BCS or Pipard coherence length. And basically, this is the size of the Cooper pair. Now, in a conventional superconductor like aluminum, this length scale is huge. It's about 1,000 angstroms. And you have many Cooper pairs within the size of one Cooper pair. And all the Cooper pairs are correlated. So if you want to break superconductivity, for example, if the Cooper pair wants to scatter on some defect, then basically you have to break all the Cooper pairs within this size of the coherence length. This is why superconductivity is so robust in conventional superconductors. The other length scale is the size of the vortex core. Here you see the vortices. That's not so clear, but basically when you apply magnetic field, the magnetic field penetrates in the form of vortex, and then this vortex has the size of Ginzburg-Landau length scale, and you can actually break superconductivity. This is type 2 superconductor. You can actually break superconductivity when all these vortices touch each other. So
What is this figure?
this is some decoration that you can look at the vortices. It's not so clear, but basically you
No, but what is it? STM measurement?
no, actually it's a photo imaging of it's a magneto-optical imaging. you can actually see the move. It's a movie. So when these vortices touch each other, you break superconductivity, and this is HC2. This is the upper critical field. So when we measure the upper critical field, we measure this length scale. And when we measure delta, when we measure the superconducting gap, we measure this length scale. So I'll summarize the question that we want to study with this tunneling experiment. First of all, what is the nature of the critical temperature? What is the symmetry? And basically, are they clean or dirty? Did I say something about it? No, I didn't. So basically, if xi part is smaller than the coherence length, it's called the clean limit. Why? Because the electron or the quasi-particle scatters on a length scale which is much longer than the coherence length, and then it has time to, superconductivity has time to recover from one scattering event to another. But when the coherence length is larger than L, it means that the superconductivity cannot recover, and this is the dirty limit. So we want to know if the electron doped are clean or dirty. So I'll summarize the results, and I won't get into details. Basically, we show that it's a non-monotonic D wave and a BCS-like, and it's a dirty superconductor. And I'll briefly show you the results. We made some junctions. Now they are not on the nanoscale, but we plan to do it that way also. And this is the tunneling measurement. Basically, this is the PCCO feature. It's SIS tunneling because of the lead. And this is when you quench superconductivity in the lead. So this is the density of states. And this is the normal state. So basically, you can apply high field and quench superconductivity and look at the superconducting feature by normalizing it with the normal state, as you do for conventional superconductors. We have some fitting procedure that I won't get into detail about. And the data is nice, and the fits are nice. I'll just go over this quickly. And these are the various doping levels. So this is very underdoped. You see a nice feature, a nice fit, and you see the lead phonons. And the same thing for 0.15. This is optimum doping and overdoped. And we can also go to higher temperatures and still fit the data very nicely. So this is 4K, 6K, and then we cross the lead superconducting gap, and this is 12K and 16K, and the fit is still nice. And the graph actually follows the BCS prediction. These are two samples followed as a function of temperature. So everything is nice. And it's a BCS-like transition, so there is no some kind of fluctuating phase or something. It's weak coupling and a non-monotonic D wave for the whole doping temperature range. And is it dirty or clean? So basically, we can extract this Ginzburg-Landau scale from the HC2 measured by the tunneling, and we can extract this Pipard length scale. And then we can extract the mean free path by using this relation for dirty superconductors. And this is L. It is tiny. And these are these two length scales. So basically, the main conclusion is that these materials are dirty superconductors. So the interplay between because of this large coherence length, actually, and the short mean-free path, TC, may be low in these compounds compared to this to the whole doped superconductors when the coherence length is much shorter. Okay, this is a summary of results that you may or may not be interested in. So basically, there are a few questions to solve, and these are the conclusions, which I already mentioned. There is some feature that should be seen. if it's a non-monotonic D wave, but we don't see it. Actually, the tunneling is insensitive to the direction. As I told you, this other parameter is sensitive to the k direction. So if you come from one side, it should be different comparing to the feature if you're coming from the other side. But we don't see that. How come D wave or other parameter with nodes survive the dirtiness? This is still unclear. So the solution is to make a local or nanoscale study that we haven't done yet, but this is a work in progress. So here's the relation to this nanoscale meeting. So we would like to make a local tunneling measurements and also to look at, to change this, to change actually the size of this Cooper pair by studying granular materials. This is work done in collaboration with Guy Deutscher and Alex Palevsky, and we will measure Nernst effect, which I'll show you in a minute. Do I have some time, or is it gone? 5 minutes. Okay, so this is just to amuse you. This is things that we would like to do. This is the work done in Jerusalem by Amos Shaoni from the group of Oded Milo. So basically, we would like to do the same thing. He's looking with STM. In his sample, he found some crack, and then he can look, and this is epitaxial film, so he can look at various directions of the grain when he moves his tip about, and he see a zero bias conductance peak here, which is typical for a D-wave symmetry, or he sees a dip when he's in the A direction. So his feature changes when it changes basically the location on the grain, but this is actually changing the k direction of the probing electrons. So we would like to do the same thing on electron-doped. This is STM data by Seamus Davis group that you've seen some other data of his. Basically, this is BISCO, and he is mapping the gap by using the tunneling density of states. So this is underdoped sample, and this is optimum doping. And you see that here there are regions of large gap, which is not superconducting gap, and some kind of grains. These are not deliberately made grains. This is just a property of either of the surface or of the cuprates. So the grains are here, and separated by a matrix of some insulating, or I don't know, some weird material with a larger gap. And when you increase doping, these grains become smaller and with less significance, with a lower concentration. So in whole-doped cuprate, the gap persists above Tc and has the momentum dependence and has a spatial dependence. And maybe it's a granular-like superconductor. So we would like to measure the Nernst effect on granular superconductors and compare it with the whole-doped. Basically, the Nernst effect, you have vortices. It's the magnetic field penetrates the superconductor, and when you apply a temperature gradient, these vortices move towards the cold end, because the vortex has a normal state core and it has a high entropy. So the entropy will move towards the cold end, and when a magnetic field moves, there is an electric field produced, and you can measure the electric field as a voltage. So there is a small voltage signal when you apply this temperature gradient, and this is how the measurement is done. You put 2 thermometers, you measure the temperature gradient, and you measure the voltage. This is, of course, done at low temperatures. And the funny things about high Tc cuprates, that you actually see this vortex Nernst effect well above Tc. So this is the Nernst voltage, this is Tc, and the Nernst voltage is still persists well above Tc. You see here it's 120 Kelvin, and Tc is only 30 Kelvin or so. So there is significant Nernst voltage well above Tc, And this may be related to this granular structure. So, okay, this is another example. So we would like to test that. And this should be a question mark. So is it a nanoscale superconductivity? We would like to do this experiment and superconductors in superconductors above TC. And the summary, some of it is speculated. So electron-doped are like hole-doped, but they have a longer coherence length, and they are dirty, and therefore their TC is reduced. Both hole-doped and electron-doped have competing orders that cause some Fermi surface reconstruction. So in electron-doped, you see that specifically in RPES, in hole-doped, you have some evidence for that from this Shubnikov-de Haas that I showed you. And they both have order parameter with nodes. And local tunneling study will clarify the questions about the order parameter in electron-doped. And hole-doped have short coherence length. This may lead to a granular structure and anomalous Nernst effect. And we would like to see that in the deliberately made granular structure and see if we can understand these peculiarities. And that's it. Just a final remark. This is the liquefier by Kamerling-Onnes. And now our liquefier came back to life after 4 months that our lab had no blood, basically. And so also thanks Olivier who fixed and all the students who fixed the liquefier. So we can make the measurements at last. And the Gilson. Yeah.
And it was highly unsymmetric.
Yeah.
This it seems strange. Is this because of the coherence length? This is the reason? Are you saying this is the reason?
Maybe TC is maybe this is the reason. I mean, this is a speculation, of course, that I allowed myself to do here, but I cannot do it in public in a superconductivity meeting. So. But this can be the reason at least for the low superconducting temperature.
And if you explain again why in N-doped you get a longer coherence length, what is the reason actually?
Actually, I don't know exactly. I don't know. This is something that we don't control. I mean, in aluminum, for example, the coherence length is huge. And in lead it is smaller. I don't know exactly. Do you know?
Any other questions?
If I understand, the basic structure is the copper oxide, and you dope it with something. First of all, does the pure copper oxide have the same crystal structure that you need for this?
No.
It doesn't.
No.
So you need the doping also to change the crystal phase?
No, you need the cuprate structure. You mean the cuprate structure is some kind of perovskite.
So formed in this type of material, but not in pure copper?
No. Copper oxide is actually an impurity in this material. We try to get rid of this.
More questions? We'll see.
I want to ask you a question which may not be the right question, but actually even the answer that this is not the right question would be valuable to me because of a friend of mine who does such things. The question is the following. If I have a cluster of atoms, suppose that they can do the order of 5,000 atoms, can I assert or say that the electrons in this cluster underwent pairing transition? Is it possible that this cluster will become superconducting? Is it a meaningful concept for 5,000 atom cluster?
Yeah, I guess when the size becomes too small, you lose superconductivity. but when you put few of these clusters together, then superconductivity can somehow recover. So if there is some intergrain interaction, then you can get superconductivity.
Well, as a matter of fact, I'm not talking about the technical state. I'm talking about something that was published in Physical New Matters last year. A person called Walter De Hare. And it actually is a subject that is debate. I'm on the side of things like what you just said, although I'm starting to doubt whether I'm not erring there. And he has a paper in which he showed that in the clusters of the ovule, as small as containing 20 to 30 atoms, there is some things that can be explained only by pairing transitions in the pairs, or he claims that only can be explained as pairing. This is experimental work. What we do is Stern-Gerlach experiments of motion in the electric field, deflection. They developed ferroelectric nature. You may know those things. And so I wonder, does it really take all the... obviously, it would exhibit itself as superconductivity if you put that and make it granular with some amount. But can I talk about people with brain that have undergone
Yeah, as you see in the, I don't have a clear answer to you, of course. I can just continue the discussion. As you see in the cuprate, sometimes things can be interpreted as pairing without coherence. So you have pairing above TC, and you see many effects like this vortex-Nernst effect, and you see some kind of a gap that may or may not be related, but at least the vortex-Nernst effect is definitely related to some sort of a superconductivity, but you don't see Meissner effect, and you don't see supercurrent. You don't see zero resistivity. So in that sense, it is possible that there is some kind of pairing, but no coherence. So
Thanks again, you all.